Okay, and welcome back to the first lecture. As long as I don't cough myself to death. First lecture, second part. This is where we actually start the chemistry in the course. We'll start with chapter 1. That seems like a good place to start. And since I'm more or less following the order in the book, we'll start at the very beginning where there's a discussion about important ideas in science. And it mentions that one of the most important ideas in chemistry is the fact, the idea that properties of substances are determined by the properties of the particles that make them up. So if you think of a substance that you're familiar with, like water, water is the way it is because of the molecules that make up the water. Those tiny little molecules that are too small for you to see determine the properties of an ocean. And that's because things like the shape of the molecule will determine a lot about how that molecule interacts with other molecules, and that will determine its overall behavior. For instance, the fact that a water molecule is bent is responsible for the fact that water is a liquid at room temperature. Most other molecules of that size and weight are actually gases at room temperature. But because water is bent, that results in the molecule being polar, and that just means that it has a positive end and a negative end. And that means that, sort of like a magnet, the water molecules are attracted to each other. And they're not attracted to each other really strongly because the molecules are small, but they're attracted to each other strongly enough to prevent them from flying apart. And that's basically what a liquid is. It's something where the attractions between the particles is moderately strong. And in water, that's true, and it's all because water is bent. Instead of a straight molecule like carbon dioxide, carbon dioxide has a linear structure. It's actually bigger and heavier than water, but it's a gas at room temperature because its linear structure means that the molecules are not polar and they have no attraction to each other. And so they fly apart, and it's a gas. So the fact that the properties of matter overall depend on the properties of the smallest particles that make them up is kind of a stepping stone to the fact that those small particles do exist. Substances are made up of atoms and molecules. So properties, that's what props means. I'll write this down because it is an important idea. Properties of substances are determined by the properties of the atoms and molecules that make them up. Seems obvious to us, but actually, for a long time, there was a raging debate over whether atoms even existed, or whether matter was exactly the same at the smallest levels as it is at the largest levels. And we'll get to that in a little more detail in a little while. For right now, we've got first section. Is about atoms and molecules. And just as an example of what I said, the properties of an overall substance depend on the properties of the particles that make them up. You can look at what happens when you make even a small change in a molecule. So a small change in a molecule can lead to a big change in properties. And a good example of that would be, say, carbon monoxide versus carbon dioxide. Just very similar, made up of the same elements, but carbon dioxide has an extra oxygen. Big change in properties though. Carbon monoxide is poisonous. Breathing even a little bit of it can kill you because it displaces oxygen from your lungs. Carbon dioxide, well, we now know that that contributes to the greenhouse effect, and so it's not harmless, but it's not poisonous. You can breathe quite a bit of it. In fact, we do breathe quite a bit of it every day. In fact, it's in our lungs right now because that's what we exhale. And so you can be exposed to quite a bit of CO2 with no ill effects. And you can also look at H2O versus H2O2. H2O, of course, is water. H2O2 is hydrogen peroxide. And if you've already put hydrogen peroxide on a cut or a scrape, you'll know that its properties are quite different from water. This stuff hurts when you put it on a cut or a scrape. And that's because it's a strong oxidizer. It's basically oxidizing the germs to death, whereas water doesn't do that. And that's a property that's determined just by that extra oxygen in the molecule. And that's the kind of thing we're going to be looking at this session in our chemistry class. First, we might want to start out with what is chemistry. And, you know, it's not just a class where you get to mix cool stuff together and blow stuff up. Since we're entirely online this semester, you're not even going to get to do that. So anyway, chemistry is a science seeking to understand the behavior of matter. I'm going to say investigating the behavior of matter. By investigating the behavior of atoms and molecules. So, like I said, the overall properties of substances are determined by the properties of the atoms and molecules that make them up. So if you can understand the how atoms and molecules behave on the smallest level, then you can probably guess how the overall substance is going to behave. We mentioned the word matter, so we might want to say, you know, what is matter? Matter is stuff. In fact, I'm going to write that down. Matter is anything that exists physically. Anything that you can touch or feel, well, I don't want to say feel, but anything that you can touch, even if you can't feel it, because some matter is very small. And matter can also be defined as anything that has mass and takes up space, which is taking up space is just what we mean when we say it has volume. So anything that has mass and volume would count as matter. And matter counts as matter even if it's extremely small. A lot of the stuff, well, a lot of the stuff you have to get used to in studying subjects like chemistry and physics is to get used to a different scale of things. Some of the things we deal with in chemistry and in physics too are very, very, very small, like atoms and molecules and subatomic particles like electrons and protons and neutrons and that sort of thing. On the other hand, some of the stuff we deal with is very, very large, like, say, the number of atoms in a handful of salt. That would be a huge number because the atoms themselves are really tiny. So that's one of the things that you'll have to get used to if you haven't taken chemistry before, is the much wider magnitude, range of magnitudes of things, as opposed to what you see in most other areas of life. Okay, section 1.2 is about the scientific method, even though it's not actually called that. It's called the scientific approach to knowledge, but that's what they're getting at, scientific method. The scientific method is just an overall process that scientists tend to use in order to formulate and arrive at reasonable and valid conclusions. Scientific knowledge, I'm going to call it Sci for scientific. Observation. My hand gets ahead of my brain sometimes. Scientific knowledge is based on observation and experiment, but especially observation. Not just reason. There is a certain amount of reason involved in science, of course, but the primary focus is on observing what happens, and then the reason can be used in figuring out why certain things happen. But the primary thing is observation. Okay, there are certain types of knowledge. You have qualitative knowledge, which tends to be, trying not to use the word qualitative, it tends to be, it tends not to involve numbers, let's put it like that. It's more about how things happen, or maybe just the general idea of what happens. Okay. Quantitative information is about how much. Or exact amounts of things. So if you're talking about numbers, you're talking quantitative. If you're talking, say, what happens or how it happens, then you're talking qualitative. Now, in everyday life, we use terminology that's not really consistent with the scientific method. A lot of times when somebody gives you some idea that you don't like, that you disagree with, you think it's half-baked, you'll say, well, that's just your theory. That's actually not a theory in the scientific method. That would be more like a hypothesis, because the hypothesis is the initial explanation for an observation. Okay, so the tentative or initial explanation for what you observed. And any hypothesis, though, will be subject to further observations and further experiments. In fact, when you formulate a hypothesis, the first thing you generally want to do is set up an experiment to test it. And believe me, in the world of science, if you don't, somebody else will. Okay, so an experiment would be an investigation of a situation under controlled conditions. And the purpose of an experiment would be to produce observations, usually in order to test or to formulate a hypothesis. Now, going back to the hypothesis, because an experiment is part of investigating a hypothesis has to be what they call falsifiable. Falsifiable, okay. And what we mean by falsifiable is it has to be testable. In other words, you have to be able to prove or disprove it. So a hypothesis that can't be tested or proven or disproven is not really a hypothesis at all. It's a belief maybe, but not really a hypothesis. If the hypothesis is disproved, and this could be disproved completely, or it could be only disproved partially. Some hypotheses are more complicated than others, and it's entirely possible to disprove part of a hypothesis while confirming other parts of it. If the hypothesis is disproved, then then you would want to modify it. Because there's no rule that a hypothesis is set in stone. In fact, in the scientific method, nothing is ever set in stone. There's always room for refining or improving the various hypotheses or theories or laws in science. So your hypothesis could be modified, and you could come up with another one, and then you could test that and see what the result is, and so on. When you have a series of similar observations, you can actually formulate what's known as a scientific law. A scientific law is just a brief statement summarizing what happens in a certain situation. And a good law will also predict future observations. Okay. And basically a law just describes how nature behaves. And keep in mind that chemicals are part of nature. So when I say how nature behaves, you might be thinking, oh, that sounds more like biology. But actually, all of this is part of nature. Even the most artificial chemicals are synthesized using natural laws. Basically, the behavior of matter is dictated by nature, not by us. We can put things together knowing that they will react in a certain way to produce a certain product, but it's actually the laws of nature that actually make those things react the way they do. Okay, so and we find that information by investigating and experimenting but ultimately it's nature that's actually accomplishing these things. So yes, let's see, also subject, this is also subject to future experiments and modification. And in fact, scientific laws can be modified from time to time. But the fact is that laws are pretty definitive, and things are usually very well established and very well supported before they come to be called laws. So it's not very often that you see a significant revision of a scientific law. Things like the law of gravity. That is really well understood. There's even an equation that allows you to calculate the exact attraction of gravity. So that really is not likely to be modified because nobody has ever found a situation that doesn't obey it. The law of conservation of mass, that when you do a chemical reaction, the total mass of the products has to be the same as the total mass of the reactants because matter cannot be created or destroyed in a chemical reaction. So it's got to be there somewhere, and if it's there and it's the same stuff, then it has to have the same mass. That hasn't been disproven either. But it was, there were a lot of experiments that went into that before anyone started calling it a law. And laws can also be known as principles. So there's the principle of conservation of mass. All right, and the one we hear a lot about is theory. Theories are actually generally broader than laws. Laws are usually pretty simple and straightforward and narrowly focused, while theories often take in sort of a wide variety of aspects of the situation. You think of something very simple like the law of conservation of mass, like I just said. All it says is that the total mass of the products of a chemical reaction have to be the same as the total mass of the reactants. That's pretty much it. Whereas compare that to something like the theory of evolution or the Big Bang theory. There's a lot of stuff involved in those. Okay, so a theory is broader. It's one or more well-supported hypotheses, usually quite a few more than one. The well-supported part is important because you don't really get to call it a theory in science until your hypothesis or hypotheses have been tested generally over and over again and found to be valid. Or, if found invalid, they can be modified into forms which are valid. And then you can actually call it a theory. Okay, a theory is okay, theory can be thought of as a model of a natural situation. Natural situation where you basically the theory tells you not only does it tell you what happens, but it tells you why it happens. Whereas a law generally just tells you what happens in a very narrow set of circumstances. And a good theory can predict, well, any valid theory actually can predict behavior beyond the original situation. So really the mark of a good theory is the ability to predict results for experiments that haven't happened yet. That's when you know you're really onto something. And theories are also tested with observations and experiments, just like hypotheses are. And like I said, everything, nothing is ever set in stone. So theories, like laws even, are always subject to revision or refinement based on, further experimental results. There is also more or less implicit mandate in the world of science that you should share your results with the rest of the scientific community. This doesn't always apply. Obviously, classified military research or trade secrets in corporate labs and things like that, they may not share those results. But generally in science, you want to share your results with the rest of the scientific community for the purpose of other people trying to replicate your results and seeing if you were really onto something, or if there was some flaw in your experiment that you didn't notice that caused your results to be what they were. And that's why there are so many thousands and thousands of scientific journals out there, because there are many, many thousands and thousands of scientists doing experiments who want to share their results. And that really helps refine scientific hypotheses and theories much faster than would happen otherwise, because the information is out there for the world to see, and lots of people will try looking into it and testing it, and they will find pretty quickly whether you were right or not. And then you can, if you were wrong, you can start modifying your theory and move on to a better one, and then you get closer and closer and closer to the truth as time goes on. A theory, a good theory, well, a theory is as close to truth with a capital T as science ever gets. And so truth basically being objective reality, what is what. With our human senses and our human perceptions, we are not easily able, in most cases, to perceive that objective reality. So we have to use our senses and our reason to conduct experiments to try to find out what that objective truth is. And that's essentially what science is all about. There is a chart in the books. This is also on one of the PowerPoints that shows a diagram of the scientific method. And you can sort of see the terms we were just talking about here. This is also in the PowerPoints, if I didn't mention that. And you notice there's a lot of going back around and around and around. And that's really what science is like. You formulate your hypothesis, you test it, you find out which parts were right and which parts were wrong. You go back and you reformulate it, and then you test it again. And then you reformulate it again, and so on and so on and so on. So there is a lot of sort of going around and around involved. Okay, so that's kind of a quick overview of the scientific method. What's also interesting about the scientific method is if you think about the steps involved in it, it's really just, those are really just the steps that we use when we learn anything, really. Even as children, when you're exploring the world around you, you do something, you notice what happens when you do that, you form an idea about why that happened, that would be your hypothesis, and then maybe you try doing it again, or you try doing it in a slightly different situation and see what happens. That's refining your hypothesis. And eventually, after a few observations, we don't call it this, but you can move on to sort of an overarching theory of why things happen, when you do certain things. And so the scientific method is really just a much more formalized and rigorous example of what all of us have been probably doing our entire lives. Okay, next section is on classification of matter. Classification. Okay, classification of matter. We already saw the definition of matter. But let's repeat it just in case. So you can think of matter as being anything that has mass and volume. Mass, on the other hand, is not the same as weight. We'll get to that in more detail in a little while, but mass is actually a measurement of the quantity of matter in an object. So the definition gets a little circular here. You notice that matter is anything that has mass and volume. Mass is a measure of the quantity of matter in an object. So we're back kind of where we started. So by definition, if it has mass, it must be matter. And another way is, of course, things that exist physically or just stuff. A term that we haven't really seen yet is substance. That's an important term in chemistry. And substance is just any particular example of matter. So, you can think of it as stuff. One thing about substance, though, is when you speak of a substance, it's kind of implicitly assumed that you're talking about a pure substance. And there's only one kind of element or compound present. It's not a mixture of different things. So an impure substance is not actually a substance at all. Technically, it's a mixture, which would not be considered a substance. A mixture would be, two or more different substances mixed together. Okay. And before we really look at matter, we have to be aware, of course, the states or phases of matter, and those are solid, liquids, and gas. Now, we're probably all familiar with solids and liquids and gases, but there are certain scientific aspects to the definitions that might be a little, beyond our everyday notice. And so we'll want to go over those. But looking at the clock, I see that we're at about half an hour again, so I'm going to stop there for now, and I'll see you in the next part. Okay?